the main purpose of the homework is teaching, not giving a grade. Are we on here? I can't.
Just a second.
Oh, we're not on. Okay, now we're on. At least the picture's on. Okay? Does David Letterman have this problem?
Yes, you're fine.
Okay. All right, so homework 0 is due Thursday. Make sure that you do it yourself. That is, you write the final answers yourself. You're allowed to talk to people, get any help you want. The main purpose is to understand the material, not to get a grade. But don't, for example, hand in correct graphs that are supposed to be based on formulas where the formulas are different, which happens all the time because the graphs are easy to see what the picture is, and then people just write down the graph even though it has nothing to do with their formula. Of course, the graph is supposed to be computed from the formula. So don't do anything that's inconsistent or makes it look like you copied from someone else. But otherwise, the important thing is to learn the material and not worry about the grade. Any questions about homework 0? Yeah.
Could you give some hints on the G and T one?
Well, I gave some hints, so can you be more explicit?
I guess I was looking for a better explanation of when you say use A and B and lambda, and which one you're using it on.
Okay, A and B are parameters, and lambda is a parameter. A and B are the limits of integration, and so when you actually have to evaluate an integral, then where it's supposed to be a number, then you're supposed to put in those parameter values. Now, also in question number 2, or in function number 2, there's a parameter lambda. So when the answer is in a functional form, leave it as lambda. But when I ask you to plot it, then you actually need numerical values. So whenever you need numerical values, use lambda equals 2. Okay, so in any case, when you need numerical values, use the A and B values that are given, which are the limits of integration, and use the lambda as 2 in the second one. Does that answer it? Okay. Okay, now the last day to drop the course is Friday, October 17th. So I want to give you feedback prior to that time. So it looks then that we'll have to give the midterm exam on Thursday, October 9th. So if I give the exam on Thursday, October 9th, then I can have it graded, I hope graded and back the following Tuesday, and then that'll give you a short amount of time to decide whether or not you want to stay in the course. And I'll go over the exam in class. So we'll discuss later what all that means. I wouldn't worry about it now, I just want to give you the date. Also, in preparation for that, I'll give you a sample exam. That is one you take home and work on, and the sample exam will be the exam that was given the previous semester. And so just use that as a way to study. Otherwise, I guess we're ready to go today, right? So the last thing we were talking about was the theorem of total probability, and I had done some examples, and then I wanted to start talking about the gambler's ruin problem. So first, let me review the theorem of total probability. So we start off with a sample space, and there's a partition, E1, B2, and so forth. And the partition means that the sample space is divided up like a jigsaw puzzle, so that the B's cover the whole space and there's no overlap. And then there's some event A, arbitrary event A, inside of there. And the question is, you want to calculate the probability of A. And we proved in class, this is the theorem of total probability. Some of these must work. There we go. Total probability. That the probability of A can be written as the probability of B1 times the probability of A given B1 plus the probability of B2 times the probability of A given B2, and so on. for all the different b's that there are. And the question is, in any application, whether or not it's easier to calculate the right-hand side than it is to calculate the left-hand side directly. So I gave some examples of that, and the examples, as usual, the strategy is that you give examples that use the theorem, and then you give and then you show that you could have gotten the answer some other way without using the theorem, so that kind of gives you more feeling that the theorem is correct. And in this case, as often is the case in this subject, the results that you got were surprising, might have been surprising, and so if they're surprising, then it's important to have additional independent verification. So that's where we looked at the case where we had an urn with balls and we were sampling one at a time with replacement and without replacement, and we calculated the probabilities associated with picking out any particular color on any particular trial. So that's what we did previously. And then I said, okay, now having done that, let's look at what's called the gambler's ruin problem. So this is another problem. Gambler's ruin. And here, the reason I want to discuss this is because this is a case in which I'm going to use the theorem of total probability, but there is not any other easy way to solve the problem. And the idea of the gambler's ruin problem is this. You imagine that you're playing this game, you're the gambler, and you have a certain amount of money, a certain bankroll. And you're playing against another player, or the house, which has a finite amount of money. And every time you play the game, each trial is like a coin toss. And at each trial, either you win $1 or you lose $1. So imagine that you're tossing a coin, and if you get a head, you win $1. If you get a tail, you lose $1. And you keep on doing this until either you've won a certain amount of money or lost your bankroll. And the question is, which occurs first? And this is sort of a pessimistic viewpoint because it's usually stated in terms of the gambler's ruin probability, the probability that he will lose all his money. And so we'll imagine that he starts out with $8, and he has, that is, he has $8 he's willing to risk. And he plays until either he wins B, that is, he goes up to A plus B, or he goes to 0. So the first time he plays, for example, his first trial, he might step up one, and then he might step down one, and then up, and then up, and then down, and so forth. So you're going to have this sequence of paths, and eventually either your path is going to intersect the top, in which case that means that the gambler wins B dollars, he quits with a total wealth of A plus B, or you're going to get to the bottom first, and in that case the gambler loses his original stake and he is ruined. There's a third possibility, which is you go forever without intercepting either boundary. Intuitively that doesn't seem like it's reasonable, and actually it's not that reasonable, so we'll just forget about it for our purposes here. So the question then is, well, let's see, first of all, there are two possibilities with respect to the steps up and down. We'll say that on any individual trial, the probability of stepping up is P, and the probability of stepping down, losing $1, is Q. And P plus Q has to add up to 1. The simplest case is when P and Q are both a half, so that's the one I'm going to consider for a numerical example. But it can be anything. And if P and Q are half, then this is what's called a fair game. Okay, so the question is, what's the probability that a gambler who starts off with $8 will get to 0, that is, he'll be ruined, before he gets to A plus B? And you can see the difficulty is that every time he either wins or loses, that corresponds to a path in this diagram. And each path could be viewed as a point in the sample space. And obviously there are an infinite number of paths. They generally have different probabilities. So if you were to calculate the probability of, say, getting here before you get to here by looking at every possible path that ends at the bottom before it gets to the top, and adding up the probabilities in each of those, that would be a very difficult job. In concept, you can see what's going on, but in actually doing it, it might be, for all practical purposes, impossible. But you can do this problem easily, or at least you can formulate it easily, using the theorem of total probability. And this is done in the book. Let's see, this particular problem is, in the book, it's example 3.14, page 90. So this is example 3.14, page 90. And the author makes more of it, I think, than is necessary, certainly for our purposes. And on page 92, he has this formula. This is the key. What he says is, suppose I let little p sub I be the probability of ruin if I am at level I. In other words, if I have I dollars and I toss a coin until I either reach this boundary or this boundary, what's the probability that starting from level I that I will reach this boundary first? And so now I apply the theorem of total probability. So the argument is simple. First of all, I have to get a partition of my sample space. So I base that on what happens on the next trial. With probability little p, I win $1, and with probability little q, I lose $1. And those events are mutually exclusive and exhaustive. So this forms a partition. So then I can immediately write down this statement. I can say the probability that I will go broke if I am at level I is equal to the probability that on the next trial I win $1. I don't like the way he used these p's so often, but I'm just using the notation in the book. So this is the probability that on an individual toss I win $1, and then I multiply that by p sub I plus 1, which is the probability that from that point on I will get ruined if I won $1 on the previous toss. Or, with probability q, I lose $1. If I lose $1, that means I drop down to level I minus 1, and then I multiply that by the probability of losing all my money if I start from level I minus 1. Okay, so this is B1. This is the probability of B1. I go up a step. This is the probability of B2. I go down a step. That's my partition. And then this is the conditional probability that if I went up a step, I will go broke. And this is the conditional probability that if I went down a step, I will go broke. And now all I have to do is solve these equations. So now it's an algebra problem, a math problem. Whether it's hard or difficult is not important for our purposes. All that matters is I have to solve this based on, well, let's see, what do I need here? I need some boundary conditions. This is my last black. Got one more here. If not, I'm going to need some a pen. These things are out of ink. Okay, so here are my boundary conditions. First of all, little p0 equals 1. In other words, the probability that I get ruined if I'm at level 0 is 1, because I'm already broke. And little p of a plus b is 0, because if I'm at level a plus b, I've already won. I quit. That's the rules of the game. And so the probability of being ruined if I'm at level a plus b is 0. I've won the game already. And then I need to solve this for all the values of I running between 1 and a plus b minus 1. So I equals 1, 2, up through a plus b minus 1. Okay, so that's it. All the probability is right here, and the rest of it is just arithmetic. Now, the author in the book tells you how to solve the problem or gives you a solution, but for my purposes, that's not important. What I'm trying to point out is that this is an obvious solution based on the theorem of total probability, but if I tried to solve this problem directly, it would be very difficult. And this is a classical kind of probability argument, this recursive idea of representing the probabilities at one stage in terms of the probabilities at successive stages. Okay? Now, let me write down what the answer is. This is what the author says the answer is. So I'll write it here. At the bottom of page 92, he says that P sub A, which is the probability of being ruined if I start at level A, and what's not included in the notation, but which I'm going to use is that he's going to play until either he wins B or he loses his A dollar. So the probability of ruin, there are two formulas for that. The first one is 1 minus P over Q to the B divided by 1 minus P over Q to the A plus B. And this assumes that P does not equal Q. Because you can see obviously that if P equals Q, then the ratio P over Q is 1, and then the both numerator and denominator are 0, so the formula is undefined. And in the simpler case where P and Q are equal, then the answer turns out to be exactly B over A plus B. So this is the case where P equals Q equals 1 half. Now, can I get another marker here? These things look like they're out of ink.
Are there no other ones in the locator there?
Only other colors, which aren't as good.
I don't think we have any more black ones.
All right, I'll try a blue one. Let's see what happens.
I'll ask in the meantime, though.
Okay. Okay, so suppose, I think this is as far as I got last time. So what I wanted to say was, here's the answer. Now, suppose that we have this gambler, and he goes to Monte Carlo, and his idea is he's going to start with $1 million. So he's willing to risk $1 million. So A is equal to 10 to the 6 dollars. And he figures that in order to pay for his vacation, he needs $10,000. So he's going to play until either he wins $10,000 or he loses his $1 million, his stake. And the question is, what's the probability that he will win his vacation if A is 10 to the 6th and B is 10,000 or 10 to the 4th? And so I think what I asked you to do is to vote on this, how likely you think it would be that he would win. And most people seem to think that it was likely that he would lose. But if you plug the numbers in, what you find is this. What I want to calculate here is the probability of winning. I'll write it like this. So the probability that he wins would be 1 minus the probability that he loses. So that would be equal to A divided by A plus B, because the probability of going broke is B over A plus B. And A is 10 to the 6th. So the denominator then is 10 to the 6th plus 10 to the 4. And now what I'll do is I'll multiply through here by 10 to the minus 4. So that gives me 10 to the 2 in the numerator and 10 to the 2 plus 1 in the denominator, which is 100 divided by 101, which is greater than 99%. So his chance of winning is greater than 99%, which I think a lot of people probably find surprising at first. So, did I say this last time? Did we get this far? No. Okay. So how many people are surprised? Nobody surprised? Okay, I'm surprised. All right. The reason, if you are surprised, the reason is that that the diagram is sort of misleading, because the way I drew it, A and B, or A and A plus B, are farther apart in the diagram than they actually are. This is 1 million, and this is 1 million plus 10,000. Because remember that 1 million is 100 times larger than 10,000. So that means that if I did this to scale, this distance here would be only 1% of the distance, and the distance here would be 99%. But what does that indicate? Does that mean that there's some strange thing going on here? And the answer is, well, no, because what's happening here is this says that the probability that he wins is roughly 100 times out of 101. So that means that 100 times he wins $10,000, and 1 time he loses $1 million. But 100 times 10,000 is 1 million, so in the long run, his losses and his gains are going to come out to be the same. They're going to cancel each other out. This is, as I said, a fair game. In other words, in the long run, it doesn't make any difference. But in the short run, since he's very likely to win on any individual trial, more than 99%, then it could be, very likely, you would expect that if the gambler is willing to risk his $1 million to win 10,000, then he could do this, for example, 20 times over his life. He could, for 20 years in a row, he could go to Monte Carlo and get a free vacation with high probability. Because each time, the chance is large that he'll win this relatively small amount of money, but eventually, one time he's going to lose, and all those things are going to then cancel out. So, the numerical values are kind of interesting. It's often true in probability, as I keep on stressing, that the answers are different from what you intuitively expect until you think about it. But the main point I want to make is right here, namely that this is a difficult problem which is formulated easily by using the theorem of total probability, and then after that it's simply mathematics. It has nothing to do with probability once you get the equations written. Okay, so that's the famous gambler's ruin problem. There are lots of versions of it, lots of different kinds of questions you can ask. Any problem that you see in the book that has a title, like the gambler's ruin problem, if you go to other books, you go to the web and look that up, you'll probably find lots of references. Okay, any questions about that? Yes?
I actually could understand how you came up with that formula. Like the formula over there on the top.
This formula?
No, the other one, PA.
This one?
No, on the other board. Yeah.
Oh, this is obtained by solving these equations. Just like the Fibonacci problem. For example, with the Fibonacci problem, remember we wrote some equations, and then I said if you solve them, you get this square root of 5 stuff in there. Well, this is the same kind of thing. So if you were to read the book or take a course in discrete math, these are just difference equations. And there are standard techniques by which you solve them. In fact, you can go backwards. You can take the solution and show by induction that if you substitute the solution in the original equations, that it works. So actually solving the equations could be difficult, but it's beside the point for this course. The important thing is understanding the formulation in terms of the theorem of total probability. So, anything else on this one? Okay, so now I want to talk about something else. It's called Bayes' rule. Let's see where that is. Okay, so we did the theorem of total probability. We discussed Monty Hall again using the theorem of total probability. And now I want to go to Bayes' formula, which is section 3.4. This is very important. Erase this, and I'm going to leave total probability up there. So this is section 3.4. And it's called Bayes, B-A-Y-E-S apostrophe. Bayes is a person. So it's Bayes' formula or rule or theorem. Those words are used interchangeably. And Bayes' formula is used to answer the following question. It's related to the theorem of total probability, but it looks at things from a different point of view. In the theorem of total probability, what you say is this. You say, well, I have this sample space with this partition, and I want to find the probability of some event in the sample space. So what I'm going to do is I will write the probabilities of the event in terms of the conditional probabilities of the event and the events in the partition. So I'm going to use the partition to calculate the probability of A. Now I want to ask the question backwards. Now I want to say, instead of asking what the probability is that A will occur, now I'll say, suppose the experiment has been performed and A has occurred. Now, if A has occurred, since the B's are a partition, that means that exactly one of the B's must also have occurred. Or another way to say it is that A has been caused by one of the B's. Of course, that's not physical causation necessarily, but the idea is that A has occurred. We know that some B must occur. The fact that A has occurred gives us some evidence that a particular B has occurred. So the question is, given now that A has occurred, what's the probability that a particular B has occurred? All right, so there's a formula for this. This is called Bayes' rule, or Bayes' formula. And, or actually, he calls it Bayes' theorem on page 100. Okay. So on page 100, he writes the following Bayes formula. So what I want to calculate is what's the probability that, given that A has occurred, that in fact a particular B, I think he calls it the kth one. Let me make sure so I'm using the same notation. So I'm on page, So I'm on page 100. Okay. So, if I know that A has occurred, what's the probability that the particular B that has occurred is the kth one, let's say? Okay, now, first of all, let me just prove it easily. It's easy to prove. What I'm going to do is use the definition of conditional probability here. So the numerator is the probability of the intersection of B, K, and A, and the denominator is the probability of A. Now, what's the probability of this intersection? Well, now I'm going to use the definition of conditional probability again to reverse things. That's the trick here, is that I can go back and forth between talking about B given A or A given B. Because mathematically, it doesn't matter. That is, mathematically, I don't have to worry about which comes first. There's no temporal relationship here. So I'm going to rewrite the numerator as the probability of A given BK times the probability of BK. Because if I rewrite this part right here as the probability of the intersection divided by the probability of the event on which I'm conditioning, that probability cancels with this, and I'm left with the probability of the intersection. So the numerator here is exactly the definition of conditional probability. Just plug definition into here, cancel that, and get that. Now the denominator, I want the probability of A. What I'll do is I'll rewrite that simply using a theorem of total probability. So the denominator is going to have the probability of B1 times the probability of A given B1, plus the probability of B2 times the probability of A given B2, and so forth. And that is called Bayes' formula. That is, this equals this. Now notice that what's happened here is that we started off asking for the conditional probability of the B's given the A, and we wind up writing the answer in terms of the conditional probability of the A's given the B's, or the A given the B's. So we switch things around because in any particular case, it might be easier to calculate this than to calculate that directly. And I'm going to give an example of that. Notice that in this formula, the denominator has the sum of terms of the form probability of B sub I times probability of A given B sub I. And that's summed over all I, 1, 2, and so forth. So in fact, the term in the numerator is exactly one of the terms in the denominator. So that'll always be true. This term is one of the terms in the expansion of the theorem of total probability. So now it's only a question of applying. The derivation is straightforward. Okay, so he does this in theorem, what he calls theorem 3.6. On page 100. All right, so what I want to do is I want to give an example of this. And example, I'm going to take an example that's in the book, although I'm going to use slightly different numbers. I change the context slightly, but the example I'm doing, in fact, I'll tell you, it's example 6, page 105. But I'm using different terminology here, so don't worry about this until later when I'm done if you want to go back and look it up, because if you look up that problem, you'll see it's exactly the same problem, and then if you're further puzzled, you can go to the solutions manual, which is on reserve in the library, and look up the solution to that. Okay, so here's the problem. The problem is HIV testing. So you imagine that you have this test which is supposed to test for whether or not you're infected with HIV. If you test positive, then you're infected, presumably, and if you test negative, then you're not infected. The difficulty is that there's always a possibility of error. So it's possible that you could test positive, but that would be what's called a false positive, and you're in fact not really infected. Or you could test negative, and in fact you are infected, and that would be a false negative. So because there's this chance of error, that means that you can partition your sample space into two possibilities. Everybody is either infected or not infected. That's the partition, the B's. And what happens is you take the test, and the test either says positive or negative. That's the event A. And having made the observation, for example, positive, then the question is, what's the probability that the positive result was caused by HIV infection as opposed to being caused by an error? Okay, so this is a standard kind of problem. You can see this is like the rest of this course, torn from today's headlines. So this is a standard question whether you're testing for HIV. In the textbook it uses cancer, but it doesn't really make any difference. So let me write out this in detail here. Here's our sample space S. And the sample space is divided into two pieces. Everybody in the population is either HIV negative, does not have HIV, or does have HIV. And what you're going to do is you're going to have this test, A, and the test is either going to tell you that the test is either going to be positive or negative. And your question is, if it's positive, what's the probability that that positive effect that was caused, in fact, by HIV, as opposed to happening to be not HIV, but a mistake? Okay, so here's the formal statement. Suppose that the prevalence, Prevalence, suppose the prevalence of HIV infection is 0.001. That is, this is what prevalence means. That is 1 out of 1,000 people on average in the long run. 1 out of 1,000 people is infected with HIV. So I just made this number up, but it's reasonable, 1 out of 1,000. In other words, well, the reason I picked 1 out of 1,000 specifically was because 1,000 is a nice round number. It's easy to multiply things by 1,000. But it's not unreasonable as an actual fact, because you could say, well, I think that statistics show that if you pick a person at random in the population, the chance that he will be infected is something like that. What I mean by that is that you're a random person in the population, let's say. You go in, you see that at FAU they're giving free HIV tests, and let's say that you're an ordinary college student. So you have no reason to believe that you're more likely. You're not homosexual from San Francisco using intravenous drugs, for example. You're not an 80-year-old nun, on the other hand. So you're just an ordinary member of the population, and that means that before you take the test, the probability that you will in fact be infected, even though you have no symptoms, you don't know, is roughly 1 chance out of 1,000. In other words, at FAU, if we have 25,000 students, there are maybe 25 students who are infected with HIV. Seems reasonable. Okay, so your chance of being infected is 1 out of 1,000. Then you take the test. Suppose that the test comes back positive. What does that mean? Well, what it means is that your chance of being infected is now greater because that's the purpose of the test. On the other hand, it's possible that the test could be an error. So the question you want to ask is, what's the probability that if in fact I test positive, or if I test positive, that in fact I'm infected with HIV? That's the question. Of course, you could ask it about negative just as well. Okay, so now, what about these error probabilities? So this is the key here. Suppose there is a diagnostic test whose false positive rate, okay, so this is another technical term like prevalence, whose false positive rate is 0.009. Okay, so we have to understand what false positive means, which I'll get to in a moment. And false negative rate is 0.005. Okay, now I think that these are reasonable numbers for the error rates, and notice that they're different. They don't have to be different, but I made them different because one of the points that's going to come out of this is that in order for this idea, in order for it to make sense when you talk about the accuracy of an HIV test, is there are two kinds of errors. There's the false positive rate, which is the probability that the test will falsely be positive. In other words, it will say you're infected when you're not, and there's the false negative rate, which will say you're not infected when you are. And so these probabilities in general are different numbers. And that complicates things. See, when you read in the newspaper about an HIV test, that might say that the accuracy of this test is 99% or something like that. And so you got to be careful about that, because that's ignoring important information. But this analysis will show us exactly how. That's the purpose here. All right. So now the question is, what is the probability? What is the probability that a person who tests positive is, in fact, infected with HIV? Okay, that's the question. All right, I can erase this. Is there a question there? Okay, so first let me write the formula. And now the formula is this. I want the probability that a person who tests positive is in fact infected with HIV. So what I'm asking for is, what's the probability of HIV given a positive test? So in this case, the event A is positive, and the partition is infected with HIV or not infected with HIV. So there are two events in the partition. So this is easy to write the formula now. So in the numerator, I have the probability of positive given HIV times the probability of HIV. And in the denominator, I have the probability of positive given HIV times the probability of HIV, plus the probability of positive given no HIV times the probability of no HIV. So this is simply Bayes' formula right here for the case in which this is B1 and that's B2. Okay? And notice that this term is exactly the same as that term. So now all I have to do is plug in these numbers, and I'm done. So I can erase Bayes' formula right here. Okay, so any question about that? Notice that all the stuff on the right-hand side is given or can be ascertained immediately, easily from the statement of the problem. And what we've done is we've taken a conditional probability and written it in terms of the probabilities with the events and their condition reversed. That's the strategy. Okay, so now I got to write down the stuff that fits in this formula. So the first question is, what's the probability of HIV? This is the so-called a priori probability. In other words, this is the probability that a person selected at random as he walks in to take the test, but before he takes the test, is actually infected with HIV. And according to the statement of the problem, the prevalence, that's what that means, the prevalence is the fraction of the population that is infected with HIV. That fraction is 1 out of 1,000. So the probability of HIV infection for a person selected at random is 1 out of 1,000. What's the probability that, given you have HIV, that you will in fact test positive? Excuse me, let me say that again. The statement is, what I need to know is, all right, I'm going to write down what's stated here and then turn it into what I need here. Okay, so the question I'm going to ask is this. What's the probability that a person who is not infected with HIV will test positive? That would be a false positive, and that is 0.009. Okay, so that's what it means when it says the false positive rate is such and such. It's the probability that if you are not infected with HIV, the test will falsely say that you are. And similarly, we have the false negative rate is 0.005. So the false negative, that is the probability that the test will say negative if in fact you are infected. And that, by the statement of the problem, is 0.005. Okay, so this formula is Bayes' rule, and this is the input to that formula based on the statement of the problem. Okay? And now all I got to do is put those numbers in here. So let's do that. Probability that if, given I test positive, that in fact I am infected with HIV, plugging into the formula is, well, let's see, the probability of HIV is 1 over 1,000. That's that guy. What's the probability that if I have HIV, I will in fact test positive? Well, it's 1 minus this, because if I have HIV, the probability that I test negative is 0.005, so the probability that I test positive would be 1 minus 0.005. Okay, because based on the condition, the reduced sample space, if I'm looking only at those points in the sample space that correspond to HIV infection, then there are only 2 possibilities. Either you test positive or you test negative. So since this is the probability of negative, the probability of positive must be 1 minus that. So this term here is that. Okay, that being the case, this term is exactly the same as that, so the denominator is 1 minus 0.005 times 1,000, or 1 over 1,000, plus, okay, now I need this guy right here. What's the probability that I don't have HIV? The probability of no HIV infection is obviously 1 minus 1 over 1,000. What's the probability that if I don't have HIV, the test will be positive? That's a false positive, and that value is 0.009. That's this value right here. Parentheses around that. And whatever those numbers are, that's the answer. Okay? So, what did I do? I want to know the probability that given that the test is positive, that in fact that positive result is caused by HIV infection, taking into account that it could be an error because there's a false positive rate of 0.009 and a false negative rate of 0.005. So I plug these values to this formula, and then whatever arithmetic I get, that's the answer. Okay, so before I do the arithmetic, let me ask here. Let me make a scale here and see whether or not you understand what it is I'm asking. Let's make this value 0 and this value 100%. And let's say here's 50%. So this is 50%. Here's 90%. Here's 10%. So the question I'm asking is, the chance of having HIV infection is 1 in 1,000. You go in, you take the test comes back positive. It's possible that it's an error, so you want to know what the probability that in fact you are truly infected with HIV if the test says you are. That's where we stand. Now, we evaluate this probability, and it's going to give us a number between 0 and 1. How many people think that if you test positive, the probability that you will in fact be infected with HIV is between 0 and 10%? Nobody. How many people think it's between 10? What? You're doing between 0 and 10%?
Yeah.
Okay, so it looks like we have what, 4, 5, 6 people between 0 and 10%. Okay. How many people think it's between 10% and 50%? 1. How many people think it's between 50 and 90? 1. Got 1? Just 1. How many people think it's between 90 and 100? 1, 2, 3, 4. Somehow this isn't going to add up. Never does. Yeah, it never does. We got 12 people. There's about 20 people in the class. Looks like there's 8 people who have no idea what the answer is. You should have some feeling for this, right? I mean, you take this HIV test. There's 2 kinds of errors, 9 out of 1,000 or 5 out of 1,000. And you test positive. And the question is, okay, I tested positive. What does that mean? Obviously, it's supposed to mean that there's a good chance that you have HIV, otherwise there's no point in the test, right? And that's what the test is for. If you test positive, it makes it more likely you have HIV. If you test negative, it makes it less likely you have HIV. But in either case, it's possible that the test could be wrong. Okay, so 6 people think that the probability that even though you test positive, that in fact you're actually infected is less than 10%, right? 1 person thinks it's between 10% and 50%. 1 person thinks it's between 50 and 90, and 4 people thinks it's between 90 and 100. Anybody else who didn't vote want to add in a vote here? Okay, so let's figure out what it is. So now I'm just going to do some arithmetic. So what I'll do is I'll multiply by 1,000. So that cancels that, and I'm going to make this numerator 0.995. And same thing over here, that term would be 0.995. When I multiply by 1,000, then this would be plus 0.009 times 999. Because when I multiply this by 1,000, it becomes 1,000 minus 1, or 999. Then I'll multiply by 1,000 again, so I'll make it 995 divided by 995 plus 9 times 999. All I did was move the decimal point 3 places to the right in each of those cases. And then if I plug in, if I put this on my calculator, that thing turns out to be equal to, according to my calculations here, 995 divided by 9986, which is equal to 0.0996, which is slightly less than 10%. So, most people are surprised, although these people here either have really great insight or think big is small. I'm not sure which.
Or we're just quick on our calc.
Quick on your calculator. That's no fair. I should have asked this before I put these numbers down. Okay, so it turns out that the probability that if the test says you're infected, that in fact you are infected is less than 10%. So this is the correct answer over here. Because most people ordinarily pick answers usually in the upper 50% scale. In fact, most people pick over 90%, which is what 4 of you did, with a whole bunch of abstainers. This abstaining is not fair. Okay, so what's the conclusion here? What does this mean? It's a straightforward application of Bayes' rule. There's no question that the arithmetic is right. How can you square the fact that the error rates are so low, and yet the probability of being infected, if the test says you are, is actually fairly small, only about 9-10%. Anybody have an explanation for that?
There are so many people who are not infected that the error rate on that overwhelms.
That's right. Yeah, the fact is that your original so-called a priori probability of being infected is 1 out of 1,000. Now you take the test, and the test is positive, so your new probability is now roughly 1 out of 10. So you're now 100 times more likely to be infected as you were before you took the test. So the probability is changed by a factor of 100, so actually the test is very informative. But still, since your original probability was so small, 100 times it is still relatively small. Of course, in reality, if you tested positive with such a test, you wouldn't be told that you would be test positive at that point. What would happen is that then another test, maybe a more expensive or more careful test, would be made, and then this formula would again apply, but now the probability that fits in here, the a priori probability, would not be 1 out of 1,000, but it would be 1 out of 10. And the other probabilities, well, if it's the same test, and the test is random, independent from time to time, then those numbers would still be the same. So if you plugged in these same numbers, but replaced this by 1 over 10 instead of 1 over 1,000, then if you again tested positive, the probability of actually being infected would be more like 99% and less like 10%. So it does make sense after all. Now, often when you read in a newspaper, they talk about the accuracy of these tests. This is common. Someone says, there's a new test for HIV, you can do it at home or something like that, and it's such and such accurate. So the question I want to ask is now, how accurate is this test? So of course it's going to be very accurate, but I'm going to come up with a test that's more accurate and better in every way. Explain that in a moment. Okay, so here's the question which I'll call, we're going to talk about accuracy. And as I say, the same problem is stated in exercise 6, or exercise 6, I guess, on page 105, except that the numbers are slightly different, and he uses cancer instead of HIV, but it's the same idea. Okay, so we're going to talk about the accuracy. How accurate is this test? So what I want to do is I want to define C to mean correct. I'm going to calculate the probability that the test is correct. That's how accurate the test is. So now I can use the theorem of total probability to calculate the probability it's correct, because I can say, well, either you have HIV or you don't. So here's the probability of HIV, and I'll multiply this by the probability that the test gives the correct result if you have HIV, plus the probability that you do not have HIV, times the probability that the test gives a correct result if you do not have HIV. So I plug the numbers into this, and that's going to tell me how accurate the test is. So I can rewrite this. This is the probability of HIV times the probability, now let's see, if you have HIV, that means that the test, if it's to be correct, would give you a positive result. So this is replaced by the probability of positive test if you have HIV. Here's the probability that you do not have HIV. And I want to multiply this by the probability the test is correct if you do not have HIV, which means that the test would give you a negative result if you do not have HIV. Okay, so now all I got to do is plug in. Let me put an asterisk here. I don't want to use that equation later in a moment. So now all I got to do is plug in the numbers here. Okay, so what's the probability of HIV in this problem? It's 0. Wait a minute here. Yeah, let me write it this way. What's the probability that if I have HIV, the test will correctly identify that? Well, that's going to be 0.995. Because the probability of error in that case is 0.005. So this is that, and here I'll write the probability of HIV. Then I have the probability that if I do not have HIV, the test will be correct. The probability that it will be wrong, we know, is 0.009. So this, therefore, is 1 minus that, or 0.991. And so this is the probability multiplied by the probability of not being infected with HIV. So that is that, and that is that. Okay, now you can see that when I plug in these numbers, the largest value that this thing can have would be 0.995. In other words, if this is 1 and that's 0, then this would be 0.995. And if this is 1 and that's 0, this would be 0.991. So the accuracy of this test lies somewhere between 99.1% and 99.5%. I can figure out exactly what it is by simply plugging in the number 1 over 1,000 here and 999 over 1,000 here. But it's going to lie between 99.5 and 99.1. Okay? In other words, it's going to be less than or equal to 99.5. So the maximum accuracy of this test is 99.5%. But it's at least 99.1% accurate, so that sounds like it's pretty accurate. Well, it is pretty accurate, but I want to come up with a test. Here's my test. My test is 99.9% accurate. Because I remember reading in a newspaper about all of these various tests, and all they'll talk about in the newspaper is how accurate the test is, because, well, newspapers are simple-minded. They don't have room enough to explain Bayes' rule and all kinds of other stuff. I mean, Boca News talked about Bayes' rule, and who buys it? So, my test is 99.9% accurate. Here's my test. So I live in Boca Raton, which is sort of, everybody knows now, sort of the white-collar crime capital of the world. All the really good scammers live in Boca Raton. So here's my test. I say to people, what you do is you send in your sample, and I'm not even going to bother to test it. So I save a lot of money. I just take the thing, I throw it in the garbage, and I send you back a result saying you tested negative. So first of all, it doesn't cost me anything. I don't have to perform the test. Second of all, I always give good news. So how can you beat this test? Now, why is it 99.9% accurate? Well, it's 99.9% accurate because it'll be wrong only one time out of 1,000. If it's wrong only one time out of 1,000, it's right 999 times out of 1,000 because it'll be right for all the people who are not infected and wrong for the one person who is infected. So its accuracy will be 99.9%. Okay? In my test, the probability, here's my test. The probability that if you have HIV, the test will say you do, is 0. And if you don't have HIV, the test will say you don't is 100%, or 1. because it'll tell everybody that it's not infected with HIV. Okay, so when I plug in these numbers into here, then what I find is this. The probability of being correct is equal to the probability that the individual has HIV, but now this is replaced by 0, plus the probability the person does not have HIV, but now this number is replaced by 1. So in other words, the answer is the probability that an individual does not have HIV, which you already know is 1 minus 1 over 1,000, or 999 over 1,000, or in other words, 99.9%. So here's a test that's totally worthless, and yet has an accuracy of 99.9%, which is better than this test, which appears to be legitimate. So the fact that someone says that you have a test for this particular factor and its accuracy is such and such, and they don't tell you anything else, like they don't tell you what the false positive and false negative rates are, in that case, the number that they tell you is actually meaningless, means nothing at all. Of course, this is an extreme example. I just made it up to illustrate that. But it does show that the answer, the accuracy, can be anything you want it to be. The reason that this works is because the a priori probability, before you're being tested, of actually being infected with HIV is only 1 out of 1,000. So you simply ignore that. Of course, then the test is worthless, but it's very accurate. Okay, so as usual, there's more to meet the eye in this stuff. And this Bayes rule stuff is very important because, well, you can see the kinds of applications. And in fact, if you go to the web, the library, and look up things like Bayes or Bayesian statistics or anything with that word in it, you'll find that there's, in fact, it's actually somewhat controversial. There's a big argument, sort of a religious argument only, between the people who claim to be Bayesians and the people who claim to be non-Bayesians. But it goes much beyond this. This application of this formula in this context, I think, is not controversial. No, there's no question about it. Application of statistics at more advanced levels, though, does become somewhat controversial because it's very difficult to make the proper interpretation. In fact, there was an article that appeared within the past year in Science magazine in which the point of the article was that exactly this problem had been given to a bunch of people who were supposed to know. These were medical students at Harvard or someplace like that. And they were asked the same question I asked you, which was to estimate the probability that someone who tested positive for these numbers actually would be infected with HIV. And it turned out that a surprisingly large number of them, about 50% of the people, grossly overestimated the probability that the positive result actually implies infection. So it's a mistake that's easy to make until people point it out to you, which is the way it often is in probability. Okay, so that about finishes this section, and I'm ready for the next one. So any questions at this point? Oh, so it makes sense, right? Okay. I'm surprised there's no questions here. In fact, people often argue with me about this. Maybe this class, that means, what this means is this class is either much more insightful and advanced than previous classes because there's no argument. You can see right away that it's correct. Or, I don't even want to say the or. Okay, so the next topic is what's called independence. Starts on section 3.5, or section 3.5. It's a continuation. In fact, we've used the notion of independence in an informal way. So, independence, meaning statistical independence. and this is on page 106. And the idea is this. Suppose I calculate the probability of A given B. If it turns out that the probability of A conditioned on B is the same as the probability of A without regard to B, then we say that A is independent of B. So A is independent of B if. So this makes perfect intuitive sense. If knowledge of B doesn't affect the probability of A, then A is independent of B. Now, also, we could argue, you could say that B is independent of A if the probability of B given A is equal to the probability of B. Exactly the same argument. It also makes sense in terms of the meanings of the words that you would think that if A is independent of B, then B should be independent of A. In other words, these should be equivalent. And in fact, these are equivalent because what does this statement say? This is the same thing as saying that the probability of AB divided by the probability of B is equal to the probability of A. In other words, I'm applying the definition of conditional probability here. And likewise, I could do this for this statement, and I would find the probability of BA divided by the probability of A is equal to the probability of B. But the probability of AB and the probability of BA are the same. When I multiply through, then I find that what this implies is that the probability of AB is equal to the probability of A times the probability of B. In other words, this says that and this says that. So what that means is that when people often in textbooks, when they talk about independence, they define independent to say that two events are independent, A and B are independent, if the joint probability is equal to the product of the individual probabilities. However, I really don't like to start with that because this doesn't have the same intuitive appeal that this does. But this has the property that it shows immediately that if you take this as a definition, then A and B are interchangeable. In other words, if A is independent of B, then B must be independent of A. So a question that's often asked in probability is, suppose we have two events, are they independent? And the answer is, well, I can answer that by calculating the conditional probability either way and verifying that this is true or this is true, or more usually what people do is they say, calculate the joint probability, calculate the individual probabilities, multiply them. That is, if this is equal to that, then the events are independent, and if it's not equal, then the events are not independent or dependent. So then lots of questions come down to actually making a calculation of this, a calculation of this, a calculation of this. But it can be tricky because people tend to impose on the problem their opinions of whether or not things are independent. And if they think they're independent, it turns out that they always calculate this, so it turns out to be the same as that. So you have to be careful that you don't impose your prior viewpoint on it, that you calculate these things carefully. And so I'll give examples of that. Now, there are actually two ways that independence is used. One way is to say that events are independent because they must be, because there's no connection between them. And therefore, I will use that independence as part of a model for a more complicated problem. For example, I'll talk about this next time, the dice problem. You typically say that if I have two dice, the dice are independent. Why is that? Well, they must be independent, because how can they have any connection to each other? Well, maybe, maybe not. The other way you use independence is to say, well, I don't know whether these things are independent, and I want to check and see whether they are. For example, cancer and smoking. Are cancer and smoking independent? Well, now everybody seems to agree that no, cancer and smoking are dependent. That is, the probability that you smoke and have cancer is greater than, not the same thing, as the product of the probability that you have cancer alone or that you smoke alone. And why is that? Well, because cancer causes smoking. Smoking causes cancer. But the argument that I just made when I says that cancer causes smoking is one that the tobacco research, quote, scientists, unquote, used to make before they really got beaten down. But in the days when they were still trying to say that there was no connection, you could make a statistical argument that it was just as legitimate from a scientific point of view, from a mathematical point of view, to say that cancer causes smoking as it is to say that smoking causes cancer, because these probabilities don't show any causality, they just show a linkage. Okay, I'll get back into that in detail next time.